welcome to the April ECE seminar. This time, Dr. Tang will give us talk about lifelong learning. Dr. Tang received his PhD degree from University of Ireland in 2016, and he joined our department in 2017. And his research interests including artificial intelligence, statistical machine learning, data mining, information and signal processing, and so on. Dr. has been very successful in winning external proposals and published journal articles in these areas. So with that very brief introduction, I give the floor to Dr. Tang.
Okay. Yeah, thanks so much. Thanks everyone for coming my today's seminar. And this is Bo Tang, and I'm very glad to have this chance to talk about my research in machine learning and AI. And in particular, this talk I will focus on our research in lifelong learning. And then I personally believe that lifelong learning is an important step towards the building of machines with human-like intelligence. And then I hope after today's seminar, the audience will have a better understanding to this topic. So here's the outline of my today's talk. Firstly, I will give you a brief introduction to lifelong learning, talking about what is lifelong learning and then how it's different to existing machine learning. And then I will talk about several methods in literature. And then after that, I will focus on our current research with two methods. One is to learn to memorize. The other one is learn to recall. And then after that, I will talk about several challenges and opportunities still existing in this field. And hopefully, this will give us insight or direction what we should go next. So before we talk about the lifelong learning, let's take a look at what the current machine learning or AI is doing. So in recent years, we have seen tremendous success of machine learning and AI, and then the impact of modern AI is everywhere. This is mainly because the advance of deep learning or deep neural network, and then which can achieve the state-of-art performance for many challenging tasks. So the deep learning or deep neural network basically is a connection of several layers of neurons, right? And then we have MRP, it's a multispectrum neurons, and the CNN or GAN or LSTM. So those methods are very successful. Okay. Can you mute a little bit?
ওইটা হচ্ছে আমি ট্র্যাক রাখি যে কবে কবে ক্যাপসে গেছিলাম।
Okay. So so basically actually those type of learning can achieve very good performance in many tasks. For example, it can be applied to supervised learning like classification and regression, right? And or unsupervised learning for clustering and outlier detection, and also for reinforcement learning, right? For adaptive control problems. So those methods actually are also known as a narrow AI method. So they are narrow because it's basically try to solve the optimization problems for specific tasks. So for example, if you want to do image classification, right? And the input would be images and output is the label or the object ID. And then you basically try to find the optimal weight or parameters in this network so that the loss function or error function can be minimized. So basically it's try to search the parameter space so that you can get a minimal loss function, right? And then if you can formulate your problems as optimization problems, you can always get very good performance if you use a very deep network or you have a lot of data or large scale data. So actually, as the one of the Michael Jordan, one of the pioneers in AI, mentioned, actually there's no real intelligence there. Okay, an intelligence that works in the same way as a human brain. So for example, the lifelong learning capability. So the lifelong learning basically can describe the capability of a machine or a human, right? That can learn from a sequence of tasks. And then it can accumulate knowledge over the lifetime period. Okay, so that is something human can do very well, but it will present a huge challenge to existing machine learning method, because for lifelong learning, the data from previous tasks won't be available for the upcoming tasks, right? So if you have a multiple tasks, right, and then if you want to find out minimal or optimal solutions for this joint model, you have to have all the data together, and then you can search the space to find the minimal point. So if you don't have any data for previous tasks, so you cannot always find the optimal solutions. Okay, and this actually is the two figures to show that human can do very well for lifelong learning, right? So we can learn something when we was a kid, right? And also we can even learn when we are like 80 years old or 70 years old, right? And also recent neuroscientific studies showing that our brain, the lifelong learning of our brain will not decrease even actually when we was old, right? It will doesn't change with the age. So that is something we want to achieve in AI. So that is also the ultimate goal of machine learning or AI, right? So to achieve this, so we have to take some the motivations from our, like say, how our brain works. And then that is like the focus of the neuroscience studies. And it has been shown that our brain memory systems have three stages. Firstly, we have a sensory memory that can take the sensory input, for example, the vision or hearing as input, and then it can like process this data with some kind of like attention mechanisms, and we can only focus on those information that are interesting or are very important that you want to learn. And then after that, we have the short-term memory. And the short-term memory basically can do some kind of like encoding or rehearsals. And then those short-term memory only last for like several seconds or minutes. And then if you can identify some important information you want to memorize for a long-term, so those information will be stored in a long-term memory. Okay, and this short-term memory and the long-term memory can be converted over time. Okay, sometimes you just like forget something, right? And then sometimes you always want to learn something. So those actually process will be is an ongoing process in our brain every second. And then also actually our brain, particularly in the hippocampal systems, plays an important role in this kind of short-term information adaptation. And then this is also the long-term knowledge consolidation. Okay, that's where we try to convert the information, okay, the short-term knowledge and the long-term knowledge. And also in 1949, Herb actually found out a very important and very interesting plasticity and stability dilemmas. Plasticity means that how easy your weight, your brain connections will change. Okay, basically it's adaptation of your neuron connections. And stability indicates that how much you can retain your information in your brain. So that is a dilemma, because you have to find out a very nice and excellent balance between plasticity and stability in our brain. And moreover, actually, in 1995, we also have this kind of like a complementary learning systems, the theories. And in these theories, it's described like in our brain, we can model our brain actually using two systems. One is a hippocampus, the other one is a neural cortex. The hippocampus basically is kind of like a memory systems that can store the short-term memory or episodic memory. That is a series of a loosely connected event or memory. And that is a fast, it can support a faster learning to learn arbitrary information. And also we have the neural cortex. And in these memory systems, it can do some kind of like generalizations. And then that is a slow learning for supports long-term learning. And those learning systems can be, the knowledge between these two systems can be converted through like retrievers and replay. And then some information can be converted into a memory in our neural cortex for long-term memory. Okay. And this theory is very important for our method. We'll talk about it later. And that can provide a mathematical or computational models or framework, okay, to achieve the lifelong learning. So here we define like how do we formulate the lifelong learning problem. So basically the lifelong learning problem can be formulated as mathematically in this way. So basically we are giving a sequence of key learning tasks. For example, you have a task 1, task 2 to task T. For example, classifications. Every task will perform some classifications. For example, task 1 is try to classify digit 0 and 1. Task 2 is try to classify digit 2 and 3, something like that. And each of which we are provided with some data set. For example, classification, you have a labeled data set. And then the objective of lifelong learning is that we try to sequentially learn all tasks, but only the current data set at hand. So basically, actually, we have this kind of like formulation is that, so we are, for example, you already have learned like a task K, and then when task K plus 1 data set is coming, you will adjust your models so that it can learn the task K plus 1, and also it can perform classification or previous tasks. Okay. And this actually present a long-standing challenge to current or model AI method or machine learning method. And that is called a catastrophic forgetting issue. So existing AI method will have this catastrophic forgetting or interference problems. And this problem actually describes a phenomenon that when you learn a new task, its learned knowledge for previous task will be abruptly lost. And that is true because like for our previous or current AI method, what we do is that we try to optimize, right? Optimize the loss function for the current task. And just make sure you know that all the previous task data were not available at this point. So actually these two figures shows these problems more clearly. For example, actually the blue circle here is the task, the previous task, for example, the first task. And you can find out that, okay, this one is the optimal solution for this task. And then when you have a new task, actually it's where we shift this solution to another optimal solutions, right, for the current task. And then if you find out another solution for the current task, and then this solution definitely cannot be applied to your previous task, right? Because they have no common or overlap space there. And actually, and if we can draw this kind of plot, this kind of like a loss function, and you can see that once you have a new task, and then the loss function actually for the first task will be significantly increased. That indicates that you can get a good performance for the new task, but you will have a poor performance for your previous tasks. Okay. So actually, all the lifelong learning method is trying to address this issue. Okay. And then actually in literature, we have 3 types of method. One is the regularization approach. And then this approach is mainly inspired by theoretical neuroscience models. And then basically the idea here is that we will add some kind of like regularization terms in your loss function when you learn a new task. So when you actually try to shift your parameters to a new space, and then basically I will give you a constraint. You don't have to actually go to here, but you should actually go with this line so that the new solution actually will be lying on the overlap space. Okay, and then in this space, actually, you can see that it can actually give a good performance for both tasks. Of course, it may not be the best performance for all tasks, right? But it can still somehow to say, okay, we can still get very good performance for the current task and all the previous tasks. So that's the key point. And then there are several examples of method. For example, you have the learning without forgetting method, and also you have EWC. And this method basically is the EWC method. It's just like try to minimize the loss function, and meanwhile, it's try to minimize the difference between the current solutions and the previous solutions. Okay, and the F here is called this visual information. So basically, in theory, so this method can be proved that it's trying to achieve a minimal KL distance between the distribution of 2 parameters, okay, the current one and the previous one. Here, the second one method, and that is called the memory replay approach, also sometimes called the recall method. And this method basically is mainly based on the complementary learning systems, the theory we talked about earlier. And basically, it have 2 systems. One is try to mimic the functions of a hippocampus, and the other one, another system is try to mimic the function of the neural cortex in our human brain. So the idea here is that, so basically, actually, we can have this hippocampus systems. Basically, it's a neural network, and serving as this hippocampus systems, and that can learn the current task. And meanwhile, we will have another systems. It's called the neural cortex, or we can call it external memory systems, that can memorize all the previous knowledge, so that when you learn the current task, we will generate some kind of like a previous data, okay, and then we augment the current data set so that we can train all the tasks together. So basically, that is called a recall, right? So when you learn a current task, we always try to recall our previous data. And here are several examples of method. For example, we have a neural tuning machines, or the GM, the experience replay. And then here just like show the graph of this tuning machine, and I think that is a very important actually step towards the called the memory network. I think this is the first method in memory network. And this method basically is try to introduce external memory, just like our computer memory, okay? And then this AAN is artificial neural network. It can be MLP, or it could be CAN. And that is observed as a controller or CPU, right, in your computer. And this one actually will learn the current task, and meanwhile, it will actually save some memory, some knowledge into the memory, okay, just like in your CPU, in your memory, in computer memory, okay, and then it will generate some kind of like a read and a write, okay, this is a head, so that it can access the memory, and based on the current input, okay, and the whole network can be trained in an end-to-end manner. So basically, it's still, you can still consider this kind of architecture is kind of like a differentiable computers, okay? And then you can define a loss function, and then you can actually generate which memory you want to store and which memory you want to access, okay, in an automatic way. And here's more details of this method. And then the last method is a more straightforward method, okay? It's called the dynamic architecture. So this method basically is try to increasingly accommodate new neural resources in response to the new information. The idea here is pretty simple. So basically, actually, when you try to learn a new task, right, that indicate that we will have some new knowledge you want to learn or memorize. So actually, we just add more neurons or hidden neurons, okay, so that these neurons can store those new informations, and then they can integrate into your previous knowledge systems. And also, actually, this idea can have some kind of a neuroscience theories, okay, like a memory association formation in hippocampus. And then we have several methods, okay. One is the DAN, okay. You have just like a incrementally add more neurons, or actually you can do this kind of like selective neurons network expansion. So actually, when you expand this network, and meanwhile you try to actually retain some neurons, okay, and then try to enhance or try to decrease its importance to the current tasks. And then the main challenge of this approach is that how do you actually select and how do you determine how many neurons you should add, right? And it's hard to evaluate if you add these neurons and how it will be affect to your previous tasks. That is the main challenge for this kind of approach. And here, actually, I would like to talk about our recent two research in this topic. One is learn to memorize. And then this one actually can be considered as a combination of this dynamic architecture and the regularization approach. Okay, so the idea here is pretty simple. So basically, actually, as we know that we talked about earlier, so the key point try to avoid this kind of like a catastrophic forgetting issue is that we try to add some regularizations, right? So that the new solution actually will lie into their overlapped space. Like for example, if you have two tasks, you want to be here. If you have three tasks, actually you want the new solution will be lie into here, so that this solution can provide a good performance to all three tasks, right? But here's some issues. So if the number of tasks increase, what's the problem here is the overlap space will be decreased, and sometimes this doesn't exist, right? And the overlap here will be greatly decreased with the increase of tasks. And then actually this approach is trying to address this issue is that we just like try to expand the space, the subspace, the parameter subspace for each task, so that we can increase the overlapped space, and then we can easily to find the solutions. So that's the key actual idea for this approach. And how can we do this? So the one solution actually we talked about earlier is that we can add a regularization, right? And also here, our approach is that we can add some kind of constraint into the network architecture. We can add some kind of like a soft mask. And then when we learn some tasks, we can enforce some neurons that don't change. And those neurons would be important for our previous tasks, okay? And then basically, actually, we have proposed two mechanisms. One is called the synapse salience measures. And this measure basically is try to measure the importance of the neurons that will be important to the previous tasks. And we try to isolate those neurons, right? So that the previous learned knowledge will not change when we learn current task. And the other approach is that we have this structure-aware synaptic consolidation mechanisms. And these mechanisms can help us to strengthen the connection of neurons for the current tasks. So we try to strengthen those neurons that are also important to current tasks, and we don't want to change anymore. Okay, so that actually we can achieve that giving a limited number of neurons, right? The number of neurons will be fixed, and given this limited number of resources, we want to actually assign as minimal possible neurons for one task. So basically, that is the goal. And how do we do this? So basically, actually, we are mainly inspired by the optimal brain surgery theories and to determine which neurons is important. Okay, so how do we determine which neuron is important for previous tasks? So here's the idea. So one actually quick idea is that if we set one neuron connection, this WL, for example, to 0, and we want to see how the output will change, right? So if there's a large change, right, if you set this neuron to be 0, that's indicate that this neuron should be important to the knowledge we have learned. And then actually we can define this difference here. And then the larger this difference, the more important it is. Okay. And then actually you don't want to actually apply these mechanisms to all neurons and try to set one to be 0 and see the output change. And that will take this time consuming. Okay. And here we apply a tidal expansion to this error, and then we can find out a closed form solutions. And then we can compare this one with a threshold. Okay, if this one is larger than a threshold, and then we can see that is important. And then we can see we can put a mask over there, and these neurons will not change when we learn new tasks. That's the key idea. And also, actually, the other mechanisms for our approach is that we try to strengthen the connections between the neurons that is important for our current task, so that we can use a minimal number of neurons for the current tasks. And then the approach we apply here is kind of like regularization approach. We just add a momentum in this gradient descent. So as we may know, actually, when we try to find out the minimal actual loss function, right, for our optimization problem, basically we just like try to search the space, right, using gradient descent. We just like you just can imagine that there's a ball, right, and we just try to move this ball to the minimal locations. And then here actually we just apply a momentums, and this momentum can be considered as like a frictional force, right? So if this neurons is important to our current task, we just like add a force, and that's where we prevent its change from changing, okay, for our current for the later data point. And similarly, actually, we can apply a tidal expansion to this information entropy, and so that actually we can find out which neurons is important for the current tasks, and we can add this one to our momentums, and that can actually reduce the number of neurons that will be used for the current tasks. And here's some like a report. We have conduct some experiment, and then actually we have particularly we do two type of experiment. One is incremental image classification tasks, and in this task we have a user split mean amnist. That is basically is a data set try to classify the handwritten digit like from 0 to 9, and then actually we have formatted this task to be like 5 tasks. And then for the first task, we try to recognize digital 0 and 1, and the second task is try to recognize digital 2 and 3, and the 4, 3 and 4, 4 and 5, 6 and 7, something like that. And also actually that is for MRP. And also we also can be used we can use CNN. And for CNN here we try to recognize the digit, and meanwhile we try to recognize the human face. Okay, so basically actually we have a CFA10, and that is called like object detection or object recognitions. They have all kind of like animal object in this data set, and many other data set. We have mixed them together so that this CNN can recognize digit, and also it can recognize the object in this like animals or humans in this data set. Okay, and all the tasks will be given in a sequential way. Okay. And the other type of method, the experiment we have conducted is that we try to incrementally generate some images. For example, we can use the VAE variational autoencoder as our baseline model, and then we have used some kind of a celebrity face images as the baseline, so that we can train the VAE on this celebrity face images, so that this VAE can generate some face images. And latterly, we have applied anemone face images, so that it can incrementally to generate some kind of like a new type of face images. Okay. And then for the classification task, we have to use some kind of a new matrix, okay, to evaluate the performance for lifelong learning. And then one is the ACC. ACC actually is the widely used for traditional machine learning. And meanwhile, we have introduced two type of metrics. For example, is a forward transfer. The other one is backward transfer. So the forward transfer basically is try to measure the performance of learning current task. Okay, so basically how the learning of current task will contribute to the learning of future tasks. And the backward is that how the learning of current task will contribute the learning to the previous tasks. Okay, and here's some kind of like the formula to measure this kind of like a performance. And here's we have tables shows the performance. So we have compare many kind of like a method here. Okay, and the EWC and the LWF and HAT, this kind of regularization approach. And then here's the joint. The joint approach is basically the optimal solutions. And then in this approach, we assume that all the data set, the data set of all tasks are available, so that you can train on optimal solutions for all the joint models, right? So that's we can give you the the upper bound performance. And our approach is kind of like this. Okay, it's where gradually, I mean, this one is ours. Okay, this one is ours. It's very close to the joint performance using the LRP and the CNN here. And here's the for image generation. Okay, and from here you can see that. So this one actually is the result using VAE for generating this celebrity face. Okay, just a human face. And once we have trained with the another type of like face images, and then actually you can see that we have forgetting issues, right? And then the output will be mainly dominated by the new type of images. And this one actually is the result we get using our approach. Even after we learned this new type of face images, we can still generate some kind of images from previous tasks. Okay, and this result actually has been published in IEEE this journals, and we have we didn't touch many mathematical formulations of this method. So if you are interested in, you can actually refer to this paper. And here's another type of method I would like to talk about. One that is try to recall. Okay, it's kind of like a memory replay method. So that is mainly inspired by the complementary learning systems theory, as we mentioned earlier. So the idea here is pretty simple. Okay, so that is mainly motivated by the fact that the brain actually learns and memorizes with the mechanisms that can learn the current task, and meanwhile, it can generalize or it can recall some images or some knowledge from previous tasks. So for example, actually, if you actually try to, for example, if you imagine that there's a kid, right, 3 years or 4 years old kid, and then he just like try to learn to recognize a dog and a cat, right? And then, for example, he already learned how he can recognize those two animals very well. And then later you ask him to learn to recognize dog and wolf, right? So at that point, when he learned the wolf, and then he just basically tried to see that, okay, how similar the wolf it is to our previous learned data. For example, the dog, they are pretty similar. And then when he learned wolf, actually the brain will automatically to try to recall some images, right, of the dog, so that when you learn wolf, you don't want to damage the information or knowledge you have learned for dogs. Okay, so that is the key idea. And that basically, actually, we just like try to introduce a data storage or generators. Okay, if you have a data storage to store some original data set, that is called the exact replay. Okay, so you have just assume that you have a memory to store some original data set. And then you can try to mimic the operation of the hippocampus systems. And the other one is called the generative replay. And in that approach, basically, you just like try to train a generative model so that we are giving a feature, and this model can generate some kind of like a raw images or artificial images. And this image can be used to train this model. Okay. And here's the mechanisms and how do we do this. So for example, you have a text one, and then you have a model. That's a model is a try, for example, for classification. And also you have a generative model, and it's G here. And then once you have a learn task two, so basically actually we will have a new data, and meanwhile we try to recall the previous task data, okay, and then augment the current data set to learn the current task two. And later we can learn task three. And in task three, we can actually augment the data set with the data set from the task one and task two, like this. So for this approach, one main issue is that how do you determine which information should be stored in your data storage for exact replay, and then which images should be replayed for this generative replay, right? So how do you determine which images should be stored, right, in your brain? That is the key. So here we proposed call it a queued recall. Queued recall basically means that the idea here is that we just try to recall those memory with the largest forgetting or the maximum interference of confusion when you learn the current task. Okay, that is what I talked about earlier, right? You have an example, you have a learned dog and the dog, and you have a learned horse and a cow, and you have lion and wolf. And literally you try to learn cat and wolf. Okay, so when you learn cat and wolf, basically, and you give an input, right? And then you should determine which type of image should be used to train these models from previous tasks, right? And then basically we just like try to compare, okay, which brain and which memory in your brain will have most impact when you learn current tasks or current images. And we will get that images out, and then mix them with the current data set and try to train these models. Okay, so and that is also called the maximum interference. This kind of memory, this kind of approach. And actually, we have this memory here, and the memory could be data storage. Okay, that's for exact replay. Also, actually, you can generate. You can have a generative model here. Okay, so that you can generate a data set. Okay, using the features as input. So actually, here's the pseudocode of this approach. Okay, and this actually is we didn't publish this paper yet, but it's ongoing work, and hopefully we will publish this one soon, and we can get very good performance right now. So for example, actually we have do some experiment for the spread amnist dataset and or the spread 3-10 dataset, and then this approach can somehow get very good performance for some tasks. Okay. And then sometimes you have accuracy, measured accuracy, and forgetting. This is a metrics for this approach. So here's some takeaway, okay, of a current research finding. So basically, actually, we talk about like two types of methods here. One is learn to memorize. The other one is learn to recall. For the approach of learning to memorize, there's some several important things we have found. That is, so both plasticity and stability of a neural weight will play a key role to avoid these catastrophic and forgetting issues. And this dilemma actually also is a major constraint for effective lifelong learning. how do you determine the balance, okay, between the plasticity and the stability, right? How much variation you can allow a neuron change, and how much like a stable, actually you want is the neuron to be stable is also important, okay? And the other one for learn to recall, so right now the memory replay method, okay, is the current state of art, okay? It's usually can get very good performance, much better performance than other two type of methods we talked about earlier. The major reason here is pretty simple, right? Basically, actually, for exact replay, you basically try just like store many data, okay? You have just store the raw data from the previous task. So that's the reason actually you can get very good performance. And also actually recalling this important memory is very important. So we always have a constraint that the memory capacity, right? Given the limited number of memory resources, so which information you want to store in your memory, that's the key. And then here we have talk about like this kind of like contextual cued recall mechanisms that can somehow to improve the lifelong learning performance. So lastly, I would like to talk about several challenges and opportunities that still exist in this field, so that we can give us some insight or like directions, okay, for our future of research. So actually, the optimal goal of AI is that we try to mimic how human performs, right, in our brain systems. And then human actually has like a very excellent ability to learn and incrementally build knowledge over time, okay? So despite we have a significant advance in lifelong learning, but the current model of lifelong learning are still far away from providing the flexible and the robust performance, okay, compared to their biological systems, okay? And they actually here several research efforts we need to think about, okay? All human brain is a complex systems, and then we cannot use a single model to model this kind of like a complex behaviors of our brain systems, right? So we have to combine multiple methods together, okay, so that we can integrate multiple factors observed in our brain systems. And the other, for example, actually, we should consider the curriculum learning. Okay, the curriculum learning basically is that it describes the capability of learning simple concept, and then it can be applied to solve complex systems, complex problems. And the other one is transfer learning. Transfer learning basically is indicate the capability of transfer the previous learned knowledge into the current tasks. Okay, so we have many existing methods in these two approaches. And then in the future, I think it will be desirable to integrate those learning approach together into the lifelong learning. And meanwhile, actually, our brain actually has a very nice intrinsic motivation to explore the real world environment, right? So that we can acquire complex skills. So this is something we should consider, okay, in our future work as well. And then lastly, I think there's a very interesting approach that is research we are trying to do right now is try to do multi-sensor association or integration. So as a human, as we know that actually we can easily to associate sensory input from vision and hearing, right? And then for this kind of autonomous vehicles or autonomous agent, right? We also want to, those systems can fuse or integrate multi-type of sensors data as input, okay? That is could be also applied to this lifelong learning. So lastly, I would like to give a quick conclusion. I think we have almost run out of time. So basically, actually, lifelong learning basically represents a very interesting but challenging component of AI systems operating on real-world data, okay? Because the data will be changed over time as well. And also, actually, we have to think about like we need to take inspiration from this biological systems, like human brains, right? And then we talk about you have three types of methods in lifelong learning literature. So we have talked about the regularization approach, right? We have talked about the dynamic architecture approach. and also talk about the complementary learning systems for memory replay or recall. And also we have introduced two methods here. And then here, I think that will be contribute a little bit, okay, in this field. And also talk about some challenges and opportunities we would like to pursue in our future research. So next, I'm happy to take any question you have.